Hey all, some people I think have been having a little bit of a hard time with problem 41 on the homework with these elastic bands that act like a spring in a sense. And so I wanted to go ahead and try to give you guys some help working on this problem. So what we got here is we have a circus performer whose mass is given to us, who has these red elastic bands as I've drawn here, and he's going to be in these elastic bands here, getting ready to be launched off and going and landing into a net. All right, and we're asked to determine, give us all kinds of information in detail here, and we're asked to determine what the spring constant is of his bungee rubber bands. All right, so it's just like it's a spring. And so what we're going to have is we're going to have a situation where he goes from this position 1, where we see him here, to position 2 right here. Maybe I'll draw him over here. There he is. Getting ready to go flying up, and he's going to follow this trajectory I drew and land over here in his net. Okay? So that's what's going to happen. And so we have a transition from position 1 to position 2. And if we think about it, we can use the idea of conservation of energy. All right? So we can say the energy that he has at position 1 is going to be equal to the energy he has at position 2, or as we more commonly express it, is we can write it as his potential energy at position 1, or his initial, plus kinetic energy at position 1, or initial, plus any work done by non-conservative forces will be equal to his potential energy final plus his kinetic energy final. So let's start by looking at what kind of energy he has at these different places. So in position 1, we can see that he's at rest with the elastic band stretched. So he does have potential energy, 1/2 k x squared. Just so we understand, x would be this distance from here to here. So I'll go ahead and draw a line there to label that. This distance here is x. Okay, it's a little sloppy there. Anyway, you can see that this distance is x. Okay, but he's at rest, so his initial kinetic energy is 0, and there is no work done during this time by non-conservative forces, so that all of his energy he has comes from the stretching bands, and that's then going to be equal to his final potential energy of mgh, where h we can see, maybe I'll draw it in red, h is this distance here, his height that he gains, okay, plus his final kinetic energy, which he's definitely going to be moving, so he can go do his jump, so mv squared. Okay, so we're asked to find k, which is here, and let's see what we're given. So if we look at the problem statement, are we given any values? So we said that the bands are stretched by this distance here, so x is given to us as 3.84 meters. Okay, we want k. M is given to us, we see that up here. G we know. What about h? Well, h is not explicitly given to us, but we can observe, look, we have a right triangle right here, where x is the hypotenuse, and the angle here, theta, is given to us in the problem statement. There's the angle theta. So we can say, oh yeah, h is just going to be equal to x multiplied by the sine of theta. So we have h. Okay. M we already established. Yep, we know m. Okay, so if we find v, then we can algebraically just solve for k. Oh, that's cool. So how do we find what v is equal to? So for v, we have to look at the rest of the information given to us. So we're told that this distance that he travels once he's launched, maybe I'll call it d, that distance is given to us. We're told that d is equal to, seen here, 24.9 meters. Okay, so what we can do is we can use projectile motion. We know that the x distance for a projectile, so the x distance, which we've called d, is going to be equal to the initial x distance, which is 0, times v initial x multiplied by time. And if we notice, look, time is given to us. V initial, well, that's what we're trying to find, not just the x component, but the overall V initial. And we can observe that V initial x, because he's taking off up at this angle here, he's going to take off at the same angle as the ramp theta. V initial x will be V initial multiplied by the cosine of the angle, so we can plug that in over here, and so we have d equals V initial cosine of the angle times time, and so we can solve for V initial and find that it's going to be equal to d divided by t cosine of the angle theta. So now that we have that, we can take it here, plug it in for V, because the V that we're trying to solve for is needed in order to find K. And now we have this nice equation where we know everything except for the value of K. Again, X is given, H we found using the angle here, M is given, and then V we use the additional information in projectile motion to solve. So there's a lot of things that go into this, but you should be able to solve for K. Good luck, and let me know if you have any additional questions.